Okay, so the next talk is by Professor Arnav Dash from Indian Association for the Cultivation of Science, and he's going to talk about stability of clean interacting Floquet quantum matter, the emerging conservation laws. So Arnav, over to you.
Okay, so thanks the organizers for keep this wonderful conference alive in spite of this terrible pandemic. And also thanks for letting me discuss our work here. So the topic of today's talk is stability of clean interacting Floquet quantum matter. We will explain what it is as we go along. And here are the main references, which are the most recent result in these things. But I thought that the audience is really quite diverse and rich, so I should probably, instead of focusing only on these two references, give a rather self-contained description of the development. Of course, it will be a slice of it. There are enormous amount of development in this field in the last 2 decades, but I'll just give a particular slice of it which involves my works. Okay, so the plan is first I will just give the description of the setup, describe the setup. Then I'll just introduce some basic constructs and terminologies. And then I'll just give one-page summary of the whole thing. It might sound like a spoiler, but and it entails the danger of making the rest of the talk a bit boring. But I'll anyway do that because in the end, when the technicalities will inevitably come in, it might obscure the message. So I'd probably just secure it before that interference happens. Okay. So what is Floquet quantum matter? It's just a bunch of interacting quantum degrees of freedom, which is described by a Hamiltonian. And there are one or more parameters in the Hamiltonian which are driven periodically in time. So the Hamiltonian has a periodic time dependence, and the entire system undergoes Schrodinger evolution. And the field is about asking question: what happens to the system at long times? Of course, many things can happen. It's a very complex and very rich area. So we will particularly focus on one question, whether it just heats up to infinite temperature-like scenarios, because that's probably the most simplest and most intuitive fate people would think. And then the question is whether that is the case or something different can happen. So for the clean and disorder-free and localization-free, or free from other kinds of imposed constraints, people mostly believe this is the scenario. However, we will argue that this can actually be made more interesting by appearance of conserved quantities which were not there in the undriven system. So you drive the system, and then for very strong drive, you can have appearance of certain conserved quantities, local conserved quantities, which will actually stop thermalization and lead to interesting states, non-trivial steady states. So in order to study this kind of systems, we actually try to switch to a picture where we map the problem to one which is driven by a time-independent Hamiltonian, and that's very easy. We just observe the system stroboscopically after integer number of periods. So in that case, what becomes important is the time evolution operator over one period, and it's a unitary operator, so you can always write as an exponential of a Hermitian operator times I. And then this operator, and this Hermitian operator, we call it effective Hamiltonian. So this effective Hamiltonian can, in principle, be very complicated, because this time evolution within one period is governed by a time-dependent Hamiltonian, which does not commute with itself at all instances. So you have to take a time-ordered product, and that makes this object very complicated. We'll see how complicated it is. And however, after integer number of period, if you just want to track the wave function, so this is the expression, and this is exactly same with that of if it were continuously evolved by a time independent Hamiltonian H effective. but observed only at stroboscopic periods. So now we forget the periodic drive and we concentrate on a time-independent problem where H effective is our stroboscopic Hamiltonian. Of course, the first thing which comes to our notice is H effective is a conserved quantity, stroboscopically conserved quantity. And then anything that commutes with this H effective is also a stroboscopically conserved quantity. So these are the quantities which we have to identify. If we can identify a lot of most important of them, then we can actually predict a lot about what happens at a later stage, because these conserved quantities are not going to change. And if you have a complete set of them to characterize all the local conserved quantities, we can basically write down an ensemble just by extremizing the entropy subject to the conservation law of these things. Just we do like doing maximizing Shannon's entropy, we get Gibbs distribution. So this effective Hamiltonian, this can be expanded in various kind of series. We will talk about one, which is the Magnus expansion. So this is basically a high frequency expansion if you look at it. So it contains nested commutators of the Hamiltonian at different times, which do not commute for any non-trivial problem. And looking at the structure of these terms, you have two important observations to make. First of all, H effective can become non-local, because as you go higher and higher in order of terms, you get products of higher and higher number of these Hamiltonians at different times, and naturally there is a possibility that these products become longer and longer string over your local operators, and that hence become non-local as you go on. And then of course H effective can be long range, because it's an all-to-all multiplication of two Hamiltonians, so there is a possibility that can become long range. And that is, and this kind of properties, this nature of this effective Hamiltonian, which makes a Floquet problem different from a simple problem of a quench with a time-independent Hamiltonian. So it's basically like a quench with a Floquet Hamiltonian, a special kind of a Hamiltonian. So here is the summary. So we come back to the question, what happens if you drive a matter periodically with time? So first we consider simple system, free fermions, free particles, so on the lattice. And if you drive them periodically, what these guys themselves, they have first, when they are not driven, undriven system, they have one conserved quantity which is energy, but in addition to that, they have L number of conserved quantities, local conserved quantities. L of them, L is the number of particles. So they have extensive number of conserved quantities, but all those conserved quantities commute with the Hamiltonian. So if you drive the Hamiltonian, energy itself is not conserved anymore, and hence you might naturally think that this conserved quantity loses their meaning, and these quantities are not conserved anymore. So what happens to such a system? You have free particles, you are driving them, they are free to absorb energy, they will absorb energy and they heat up indefinitely. But that actually doesn't happen for any systems, integrable free fermion kind of system. They need not be really free fermion, they can have pair hopping kind of superconducting term also. This kind of system can be shown that this kind of system, if you drive periodically, they can actually have an extensive number of exact stroboscopically local conserved quantities. So the original conserved quantities are gone, but you can construct stroboscopic local quantities, again extensive in number, and that actually gives arrests the heating, and then it can go to very interesting non-trivial steady states which are synchronized with the drive. In addition to these exact conserved quantities, there is also another emergent conserved quantities. Actually, the emergent conserved quantities was observed first, like 5 years before the exact conserved quantities. So this is an approximate conserved quantities, but it's also perpetual. It remains conserved about an average value. It doesn't go away, drift away from it ever, but it's not exactly conserved. It doesn't remain exactly to its initial value. So you have small fluctuations around it. It drops a little bit. So then if you add interaction to the system and make it non-integrable, interactions means really non-integrable interactions, then of course you break all these nice structures of these bilinear infermionic systems. And then again, you say what will happen? Everything will heat up at infinite temperature like scenario. It will keep absorbing energy, and then basically entropy will go to a maximum level, and then you can describe it like an infinite temperature state. It has a serious weight of the mid-spectrum state, so it's just like a infinite temperature state if looked locally. So that's exactly what happens if the drive is moderate, and this is called Floquet thermalization. It goes to a state where each of the eigenstate of your H effective looks pretty random if you just focus locally. And then hence, if you just construct any arbitrary state out of them, this eventually dephases to this kind of state which is completely random locally. It's infinite temperature like state. But then there was an idea which was actually brought forth by a junior collaborator here. She asked what happens to the emergent conserved quantity anyway. The exact conserved quantities are of course killed. All of them are dead. But what happens to the emergent conserved quantity? So it turns out that this emergent conserved quantity actually survives if the drive is stronger beyond the threshold. There is a sharp threshold. This is about a particular model we are talking about, which is interacting and non-integrable. So there we saw that if your drive strength exceeds a certain sharp threshold, then a particular emergent conserved quantity jumps up into existence, and this actually arrests the thermalization and stabilizes the system to non-trivial steady states. So whether this is the only conserved quantity or not, or what are the other characteristics of the steady states is yet to be studied. But there is an example. It's like you take a bunch of interacting particles and shake them very hard, very strongly, and suddenly out of this chaos, the original interacting particles are completely chaotic. There is no conservation law except energy, and by shaking you are killing the energy. But then there appears another conservation law out of the shaking, which basically appears from it and stops the chaos. So this is basically the entire result here. Now, why it is surprising? You might say if your drive is very, very strong, then your Hamiltonian has a very large term in it, and it is on all the time. So you might approximately think that your dynamics is basically governed by that large term of the Hamiltonian. But this statement has a problem, because in quantum mechanics, there is nothing like a CAM theorem. It says that you really need to have a finite size integrability breaking term, which actually breaks the integrability. Otherwise, it remains somewhat close to integrability. So these close to integrability concepts are not really there in quantum mechanics. So what we expect in general in quantum mechanics, if you have a very small integrability breaking term, its effect will appear at a much larger time. So initially you will not see its effect. It will behave as if it's governed by the large term, but in long run, this will come up and eventually destroy your conservation laws. But here we somehow managed to calculate the infinite time limit of the observables. Even that infinite time limit observables, or we can also do simulations for many, many decades, 10, 20 decades for these kind of systems, which matches with the infinite time limit very faithfully. And even at infinite time, these small chaotic perturbations do not actually destabilize the system. So that's the main surprise of the thing. And another technical surprise, I'm basically giving the entire talk here. Let's later just illustrate these statements. So if you write a perturbation theory of any sort where your chaotic interactions is small, well, in this kind of setting, it's always you'll find that the radius of convergence of this perturbation theory will be basically zero because of many body theory. So if you go in higher order of perturbation theories, the number of processes explodes, and then the norms of these terms become bigger and bigger. So in general, you might just think that there is no way to say that there is a particular size of the big term after which the the series will become converged, and you can truncate it faithfully and call the remaining Hamiltonian approximately local conserved quantity. But there are a lot of work by many people, including Anatoly, who showed that actually this is not so straightforward. And so these divergence series are actually doesn't necessarily indicate that everything is going to be chaotic, and the H effective will actually be a very, very non-local operator. So the story goes like this. So we start with a simple Ising chain. It's a transverse Ising Hamiltonian interactions in the x direction. We drive the Z field. And we see that at the time, of course, there was no concept of this emergent conservation laws. So people usually thought that if you keep on driving, eventually it will keep absorbing energy and everything goes to zero, and how it relaxes or if it shows hysteresis was the point. But contrary to that, it seems that it stabilizes to many interesting non-trivial average, about some non-trivial averages, depending on how the frequency and the behavior with the frequency is also weird. They have some peak value structures for certain frequencies. It freezes very strongly, and then if you increase the frequency, the average goes down and then goes up, and it's like this. So initially it was a numerical observation, and then in this particular case we can actually do the infinite term wave approximation. And these are the analytic results are in the green, and the black are the numerical results for 10 to the power 5 system size. So we see it doesn't heat up to infinite temperature. So and then there is this average magnetization emerges as a conserved quantity. In fact, in this particular case, for when this Bessel function goes to 0, we have our first order rotating wave approximated Hamiltonian basically vanishing. And then there should be other higher photon processes which we completely ignored, but apparently they do not contribute anything in this process. So of course this raised the question why energy is not absorbed. People were not very comfortable with this result. First of all, they don't believe these things can remain really frozen to this limit for very weird, strange frequencies and for very, very long time, actually for infinite time, and for very long systems. And also the frequency is not showing a sensible monotonic behavior. So if you drive very fast, system should freeze fast because it gets lesser time to respond, but that's not happening. Later we argued, there was an experiment on this paper, and there we argued that this actually essentially happens because of the interference of the Stuckelberg phase of each momentum mode in the momentum space. They become two-level systems. In any case, we tried to understand this problem and resorted to a more general setting of this kind of bilinear infermionic Hamiltonian. This spin Hamiltonian can be mapped to one particular kind of this. And then we realized if we try to drive this periodically, then, and we resort to Magnus expansion, the one we showed, then all these nested commutators, since if the original Hamiltonian is bilinear, the nested commutators all reduce to operators which are bilinear. So eventually your H effective has a series which has bilinear operators in each order. Nonetheless, they have coefficients which can be big or small depending on how you're driving the system, what are your perturbation strengths, etc. So if the Magnus expansion converges, then you can basically write the effective Hamiltonian as a bilinear one, and we can immediately diagonalize it using Jordan-Wigner. And then we got a bunch of conserved quantities. These are the conserved quantities. Of course, these fermionic operators are extremely complicated in terms of the original fermionic operators. Nonetheless, we can construct these, and these are our, and we can evolve them using your evolution operator and construct these time-dependent quantities. These time-dependent quantities are obviously very interesting because they are, first of all, they are stroboscopically conserved, and second, they are exactly conserved. I mean, they are stroboscopic, time periodic, and also conserved because the wave function changes, the operator changes time periodically, but their expectation value remains conserved. So we conjectured that we can, this is all the set of conserved quantity we need, and we can just to go in the path of extremizing the von Neumann entropy subject to these constraints and construct a Gibbs ensemble which is periodic in time. And we haven't shown the results here, it's there in this paper. It absolutely accurately describes the stroboscopic behavior, long-time stroboscopic behavior of a bunch of systems. Numerically, we tested that. And of course, if the Magnus expansion doesn't converge, then there is an interesting thing happens, that all these Lagrange multipliers, they tend to go to 0. And again, you have an infinite temperature like scenario. So everything kinds of heats up within this integrable structure, which means so each of your momentum space, these two-level systems become equally populated and have the maximal entropy for that. So we understood this much, but this doesn't tell us about the emergent conserved quantities. These are all exact conserved quantities, and that magnetization which we saw here, the average, it's an approximate conserved quantity. So these conservation laws actually do not capture it. It survives, cannot explain it within this framework. And we asked obvious question, what happens to this when you put interactions? So in order to do that, we actually take a nearest neighbor interactions in this model, which breaks the integrability, and also a field in the x direction, which breaks the integrability. And then we try to study this problem. This is a non-interacting, non-integrable problem. And the transverse field is still the kind of perturbation because everything is x and that's in z. So what we observe in this case is, if you study these as a function of your drive amplitude for a fixed frequency, its frequency is actually pretty low, 0.1, so that it's smaller than your local bandwidth, which is of the order of j and k. We see this even this in this low frequency, we see this, there is a very sharp threshold. So if you increase your h, your final, this is a magnetization of the diagonal ensemble, which is the infinite time limit of this evolution. You see that it remains 0, and then it suddenly jumps. Of course, there is a very ragged things, intermittent ragged jumps, which are higher order resonances. We'll come to that in the end. And then it stabilizes. So after your field value crosses, drive value crosses this particular threshold, your final magnetization is almost close to the initial magnetization. And another interesting thing, if you do the log plot of this and try to pinpoint the threshold, you will see that the threshold doesn't move with the system size, but the curve becomes sharper and sharper. If you plot the magnetization here, focus on this part, you will see that if you increase the system size, the magnetization goes up actually. So this part goes up and this part goes down. So it becomes a more sharp, like a fast order transition. Albeit there are these intermittent drops and jumps of the magnetizations. So it doesn't get debilitated with increasing system size. Rather, it gets enhanced, and the threshold doesn't move with the system size. So then we try to see what happens as a function of frequency, and then we find the same kind of peak value structure which we observed in case of our non-interacting systems.
Arnab, you have 5 minutes.
Okay. Okay. So yeah, really should. Sorry. Yeah. Okay. So if you plot the magnetization of these Floquet states, then for these peak frequencies, you see they have exactly the structure of the x basis states, which are the eigenstates, simultaneous eigenstates of all the Pauli X operators, basically what we expect without any transverse field. So magnetization appears as an emergent conservation law here at the freezing frequencies. But if you start with one of the x eigenstates, they can have a lot of dynamics, as you can see if you track the entanglement, how the entanglement grows in this particular for this particular initial state, and only if the if for certain states like the all-up states where there are only one element in this sector, you see that entanglement doesn't grow at all. But if you are here, like in this sector, this is all up and all down a single domain state, you will see the entanglement grows basically a lot, extensively. It goes to a volume law. So that means it mixes within these sectors with the same magnetization, but it doesn't mix states with different magnetizations. So the magnetization is conserved, but there is a mixing within the same magnetization sectors. So there are various other models where we can see this. Other kinds of model with 3-spin interactions or long-range interactions, we see the same phenomenology. And the system size dependence also doesn't show any significance difference. So again, we are in the tight zone. I don't want to get into the details of this theory. It's a Magnus expansion, but in a rotating frame, because this simple Magnus expansion cannot catch even the first order term. And if you do that, surprisingly, independent of what kind of Ising interaction you take, all your first 2 order terms vanishes. So it's true for any kind of Ising model. You take an Ising model on a 2-dimensional, 3-dimensional lattice, put any kinds of interaction between them. Doesn't matter. The first 2 order terms vanishes. And for the Heisenberg model of any kind, even more interesting thing happens. In the first order, there is a term, but this term also respects this conservation law. It commutes with a sigma x. So basically, in the first 2 order, we have this conservation law intact. And then comes the most interesting part. We did a perturbation theory. This is the last slide. So the interesting thing is this perturbation theory is a first order perturbation theory. And of course, higher order terms eventually diverges. It's a divergence series. But the first order perturbation theory captures all possible dips we can see as we vary the parameter H0x. If you vary the parameter H0x, there are resonances in the theory. And those resonances corresponding to these dips. At low frequencies, all of these dips are captured by the first order resonances. This is very, very strong indication that our series is actually an asymptotic series. If it were not an asymptotic series, if it were like a convergence series, then of course this wouldn't happen. Higher order perturbation series resonances would appear because those terms were actually relevant. If the higher order terms are relevant, the higher order resonances are also relevant. But this gives a strong indication that this is not the case, and probably there is a possibility that this persists even in the infinite size, because these results, these perturbative results are, of course, for any size, any arbitrary size. So, okay, that's basically it. Thank you very much for your attention, and conclusion and outlook are actually discussed in the introduction. So I'm done. Thank you very much.
Okay, thank you, Arnav, for a very nice talk. So we don't have much time, but maybe for one quick question or two. So anybody? Okay, I don't see a raised hand. So let's then move on to the next talk in the interest of time. So Srijit, could you please share your transparency, your slides?
Yeah. Can you? You're able to hear me, right?
Right.
And
yeah, okay, it's coming up. Just
I don't know if you can see my screen.
Yeah. Okay.
No,
slow.
that's not good.
Well, it's a, yeah, now I see it. Could you just make it full screen? Yeah, perfect. Okay, so the next talk of the session is by Srijit, who is from ISR Pune, and he's going to talk about dynamics and transport in chiral clock model. So, Srijit, please go ahead.
Okay. And thanks, Krishnendu, and thanks to the organizers for giving me the opportunity to give this talk. I happened to come to the March meeting, so I decided to spend a few days here. So because of the time zone difference, I'm finding it very difficult to attend the rest of the talk. But yeah, sorry about that. Okay, so I'll be talking about some studies, numerical studies on dynamics and transport in the chiral clock model. There is a broad set of results regarding these keywords in these three papers. I have selected a set of results focusing on one particular aspect from these papers to present in this talk. Yeah. So this is the plan. I'll introduce the chiral clock model, then discuss a few basic ideas, the domain wall types and their dynamics at low densities in the ordered phase. And I'll discuss domain wall scattering at the boundaries, and then discuss the effect or some implications on entanglement growth near the boundaries after a quench from an ordered phase, quench into the ordered phase from a completely ordered initial state. And then from there, I say something about its implications on post-quench thermalization at the boundaries. In the second part, I will discuss, I'll briefly introduce the idea of using MPS, matrix product state simulations to mimic open quantum systems, and then discuss integrable points on the phase diagram, or at least point out what the integrable points on the phase diagram of the Z3 chiral clock model are, and then present the results for energy transport exponents as a function of the parameters in the model. Okay, so I'll give a very quick introduction to the chiral clock model. The chiral clock model is easiest to explain by juxtaposing with the transversal Ising model. The transversal Ising model has an
Srijit, it seems that there is some audio problem. Could you are breaking up.
With I see.
Okay, this is better.
Sure. Okay. Hopefully,
Yeah, this is better.
Let's continue.
Yeah.
Okay. Maybe I'll come close to the mic then. So the sigma z operators here are diagonal matrices, the Pauli sigma z matrices in the transversal Ising model. You can think of this as a diagonal matrix with square roots of unity along the diagonal. In the Z3 chiral clock model, the sigma dagger operator or sigma operators, which appear here in place of the Ising interaction of the transversal Ising model, they are essentially the cube roots of unity. Diagonal matrices with diagonal entries being cube roots of unity. Now that makes it not Hermitian, so the interaction has sigma dagger sigma plus a Hermitian conjugate term. That generalizes the Ising interaction in the transversal Ising model. The sigma X operator in the transversal Ising model is essentially the sigma X Pauli operator, but I can think of that as a permutation matrix, cyclic permutation matrix. And in the chiral clock model, that is replaced by a tau, a cyclic permutation of three objects in this matrix. And when you carefully analyze this Hamiltonian, it turns out that the most general Hamiltonian, which and if I write down a Hamiltonian like this, you can see that it's Z3 symmetric. It can be checked. I'll mention that again in a moment, but one could ask, what is the most general Z3 symmetric Hamiltonian? What can I do to the coupling constant such that I get the most general Z3 symmetric Hamiltonian? It turns out that allows me to keep the coupling constants to be complex without breaking the Z3 symmetry. So in going from the transversal Ising model to a which is Z2 symmetric, to something that is Z3 symmetric. The most general Hamiltonian, translationally invariant Hamiltonian that I can write down is this. Now coming to the Z2 symmetry. So the transversalizing model is Z2 symmetric with Z2 symmetry parity operator that commutes with the Hamiltonian. It is a product of the sigma X matrices. Correspondingly, the Z3 symmetry, which commutes with the chiral clock model Hamiltonian, is this operator, and it is a Z3 operator because this operator product over tau can take has three different eigenvalues, 1, omega, and omega squared, where omega is the cube root of unity. Now, if I work in the basis of sigma operators, work in the local basis made up of sigma operators, then I can think of the basis states can be written in terms of the local basis of the sigma operators. Now, because the system has a Z3 symmetry, and just like there is a Z2 symmetry breaking in the transversalizing model, there can be a Z3 symmetry breaking in the chiral clock model. And this happens when the coupling constants, the spin-spin coupling or the clock coupling constant is much larger than the transverse field term. In that case, there's a Z3 symmetry breaking. In the regime where the parameter theta is between 0 and pi over 3, there are three possible ordered phases, which can be thought of as 1, 1, 1, 1, omega, 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 and omega bar, omega bar, omega bar, etc. In the regime where theta is greater than pi over 3, you get some kind of twisted ordering. In general, for general values of theta, there are incommensurate phases also. Now, at large values of the transverse field term, that is J over F much less than 1, and there is a paramagnetic phase. And the symmetry broken phase that I mentioned here can be related to a topological phase of a Jordan-Wigner transformed degrees of freedom, which can be thought of as a parafermion chain. So the bottom line is that the Z3 symmetric chiral clock model forms a nice generalization of the transversalizing model. In the process of generalizing this, we get additional parameters theta and phi, which are not present in the transversalizing model. The talk will be an attempt at developing an intuition through numerical results, developing an intuition about what this parameter theta does in the dynamics and transport in the chiral clock model. Okay. Now, one more comment, since I'm comparing with the transversalizing model, after Jordan-Wigner transforming these models, I can get new transform variables. In the case of Z2 symmetric transversalizing model, these are Majorana fermions, and in the case of chiral clock model, these are parafermions. But the key point that I wanted to make is that if I take the commutator of H with psi, I get a linear function of the psi's, the Jordan-Wigner transformed variables, which means that I can diagonalize this commutation relation and obtain ladder operators with which you can solve the transversalizing model. In the case of the Z3 symmetric model, if I consider the commutator of the Jordan-Wigner transform variables with the Hamiltonian, I get a quadratic function of these same variables, and it is not easy to invert this diagonalize this relation, and therefore ladder operators cannot be easily constructed. And this gives a sense that the model is not exactly solvable. So while the transversalizing model is exactly solvable, which gives us the opportunities, like for people like me, to do numerical studies rather than do analytical studies on these. Now, the Z2 symmetric model has parafermionic edge modes when thought of it from the Jordan-Wigner transform variables perspective. In the Z3 symmetric model, the situation is slightly more complicated. You can try to construct the zero modes perturbatively, but it doesn't always converge. In general, zero modes are present only at low energies. So these systems are said to have weak zero mode, which means that low energy. Sorry, what I meant to say here is low energy states are doubly degenerate, whereas high energy states are not. This is unlike the transferalizing model. Okay, so coming to the domain walls. Coming to the case of the domain walls, there are 6 different flavors of domain walls here. As you can imagine, these are the domain walls between the different ordered faces. Now, what does theta do? Theta creates an energy difference between opposite chirality domain walls. I can think of a domain wall of the form 1 omega, 1 omega, and a domain wall of the form omega 1. In the case where theta is equal to 0, the energies of these different kinds of domain walls are identical, whereas when theta is non-zero, these different domain walls have different energies, which makes the theta a chirality parameter. Now, the second complex phase in the model, the phi that goes with the transfer field term, this acts like a magnetic field for the domain walls and breaks time reversal invariance. There is very little studies on the effect of phi in the dynamics of this system. We will also focus on the theta parameter, understand the effect of chirality, and we will set phi equal to 0 in the rest of the talk. Okay, so in the to get an understanding of what theta does, we will look at the dynamics of the domain walls in the weak density regime. That means that that these domain walls do not come close to each other. In that case, I can think of the dynamics of the domain walls as forming a tight binding model. So at least in the weak F regime, I can do at first order perturbation theory, and in the first order perturbation theory, the dynamics of the domain wall essentially boils down to that of a tight binding model. The chemical potential, the energy of the domain wall, is given by this mu, and the plus and minus corresponds to different chiralities. So as I mentioned before, if theta is non-zero, the opposite chirality domain walls have different energies, and that you can see explicitly from here. This essentially is like you can think of this like a chemical potential for the domain walls. And at first order perturbation theory, the transfer field term essentially scatters the domain wall from one point to the adjacent point. So it is a nearest neighbor hopping hopping tight binding model that you get when we look at the dynamics of the domain wall, single domain wall in the weak F and small density limit. Now, because the domain walls have different chemical potentials, if I look at the dispersion of these isolated domain walls in small theta regime, you see that the domain walls have blue and in the regime of large theta, the dispersion of the opposite chirality domain walls are far separated. Okay. Now, with this idea in mind, we can ask what happens at the boundary of the system. What happens to the domain wall when it hits the boundary? Again, with first order perturbation theory, you can see that the boundary can do two things. It can take if a domain wall approaches a boundary, it can scatter back as the same domain wall, just scatter, bounce back, or it can scatter into an opposite chirality domain wall. So, for instance, if 1 omega domain wall hits the boundary and scatters back into 1 omega bar domain wall, which has an opposite chirality. Now, because the dispersion relation for the two domain walls is different from each other when theta is large, as shown in this cartoon, you can see that at the boundary, I can think of what happens to a domain wall is that it hits the boundary. if theta is small, it yeah. So if theta is small, there is no chirality change, and the domain wall just scatters back. And if oh, sorry, I wrote it incorrectly. If theta is small, there is a chirality change, and if theta is large, then there is no chirality change. So I reversed the order here, and that explains the. With that, we can explain the entanglement growth properties at the edge. So we'll consider the scenario where there is an ordered phase. And oh, by the way, the bottom line of this is that as chirality theta changes, the scattering properties of domain walls at the boundary changes. In one limit, the domain wall scatters into an opposite chirality domain wall, and in the other limit, the domain wall scatters into the same chirality domain wall. I think that's the bottom line. Now, with that in mind, we will ask what happens to entanglement growth after a quench from a fully ordered phase. So let's say I have a fully ordered phase, a fully ordered phase in the system, and let's say something like this, and I switch on F. So I have all the spins pointing in the same direction, and then I quench by switching on F in the Hamiltonian. And the semi-classical picture is that the opposite chirality domain walls are nucleated from every point in the chain, and these domain walls propagate in opposite direction, and in far separated subsystems get entangled with each other as these shared as the domain walls that originated from the same point enter these far separated subsystems. Okay, so to get an idea of what, to get a qualitative picture of what happens at the boundary, I have a simplified picture here. I have a state which contains the original initial state together with in a linear combination with a state in which there is a domain wall that is traveling towards one direction. So in the actual system after a quench, there'll be a large number of domain walls that will be propagating. But right now, for simplicity, I'll just show two states. One is the initial state, which is in a linear combination with a state in which there is a domain wall that is propagating to the right. Now, as time progresses, the domain wall moves towards the edge. Now, if I look at the subsystem close to the edge, in this, before this domain wall enters the subsystem is in a pure state, because if I take the reduced density matrix of this blue box, then the reduced density matrix is that of a pure state. As time progresses, the domain wall, at some point, the domain wall enters the subsystem, and this makes the system not a pure state, and therefore the entanglement entropy increases. And in an actual system, there will be a large train of domain walls that keep entering the subsystem, and therefore the entanglement entropy turns out to be linearly, they linearly increase with time, which we can numerically see in our DMRG calculations. Yeah, now let's proceed further. As time progresses, these domain walls further move inside the subsystem. At some point, it hits the boundary, hits the edge, and then it reverses direction. And let's assume that the domain wall does not change the chirality. Then it just bounces back in the same with the same chirality. And once it leaves the reflected domain wall leaves the subsystem, the system again goes back to a pure state. In an actual system, what happens is that the entanglement grows, and at some point it saturates because of this, because of the domain wall leaving the subsystem. Okay, now we'll ask what happens if domain wall is reflected into a different chirality. The domain wall hits the boundary and it reflects as a different domain wall. And now, even though the domain wall left the subsystem, it turns out that the system is now in a mixed state. It's a mixed state of omega state and omega bar state. And this means that the entanglement continues to increase even after the domain wall leaves the subsystem. And this can be seen in DMRG calculation. And this is the first point that I wanted to mention about our result. So the left-hand side shows a cartoon of what happens to the domain wall. Let's say there is a ordered face B, and there is a domain wall between A and B domains that move rightwards, hits the boundary, then it will scatter. If it scatters into a different domain wall, which is of the form AC, then what happens is that at the boundary, this graph shows the plot of time versus the entanglement entropy in a subsystem at the boundary. Initially, the entanglement grows linearly because of new domain walls entering the system. And as the domain walls start leaving the subsystem, the entanglement continues to grow because of this mechanism that domain walls flip chirality at the edge and leave the system in a mixed state. And therefore, the entanglement continues to grow. In the case where the domain walls just bounce back into the same chirality, then the domain wall, something like this, where AB domain wall scatters back as AB domain wall. In those scenarios, the entanglement grows linearly initially and then flattens out later. Now, this may be a minor point, but the more interesting thing is that this implies that the edge is thermalizing in the first case and not thermalizing in the latter case. So for small theta, where the chirality of the domain wall can change upon scattering, we find that the edge thermalizes. So I have this plot shows the magnetization at the near the magnetization of the chain as a function of position. And this is after a quench. Okay, so the earliest time is where the magnetization is 2, and after quench, as time progresses, the magnetization keeps decreasing as I have quenched the system, and the system is trying to go to a high temperature, effective high temperature. And you can see that the boundary spins are also slowly thermalizing. Its magnetization is decreasing. In the case where theta is large, the system fails to thermalize because of the mechanism that I mentioned. And you can see that the spins at the boundary are retaining its initial value after some decrease in the magnetization. So the outcome of this mechanism is that the boundary spins fails to thermalize if theta is large, and boundary spins do thermalize if theta is small. Here, of course, it's a numerical study. I cannot say eventually whether it will thermalize, but at least within the numerical timescales, we can say that when theta is finite, the system doesn't thermalize. The system thermalizes very slow. Now I'll briefly say something about a second result. I will not go into great details here. If there are questions, I'll be happy to answer at the end. So the second question that we asked to understand the effect of theta, the chirality parameter, was to understand energy transport as a function of theta. The broad question is, how in high temperature phase, where we have algorithms that can determine transport properties, how does theta affect the energy transport? And the strategy is very simple. So this idea is originally due to Thomas Prosen. The idea is to use a Lindblad coupling to mimic baths at the two ends.
These baths are... your 5 minutes.
Okay, yeah, that should be sufficient. Thanks. I have Lindblad operators at the edges, and these Lindblad operators are set such that the effective temperature is beta 1 and beta 2. And what are these effective temperatures for? It's for a Hamiltonian that is local at the edge, and the Hamiltonian needs to be as close to the restriction of the original chain Hamiltonian to the edges. So I set the Lindblad operator such that there are two different temperatures maintained at the edges, and I look at the energy current in the steady state, non-equilibrium steady state realized from the solution, long-time solution of the Lindblad equation. And the strategy is simple. Most of you, or at least some of you, might be familiar with the usual way to think about operators and states as matrix products. So you can think of the density matrix as a matrix product operator with some in-state legs and out-state legs. The strategy to do simulate time evolutions for the density matrix is to take the out legs, twist it into merge it with the in leg, and such that I have a multi-index representing the in and out state of the density matrix. And so the density matrix can be thought of as states in a space where the local Hilbert space dimension is d squared, where d is the actual physical Hilbert space, and density matrix can be thought of as a matrix product state where the local Hilbert space has a dimension square of that of the dimension of the actual physical system. And once I have this, I can exponentiate the Liouvillean and apply that to the density matrix. And the calculation and the techniques that are needed to do this are standard, and these are just time evolution techniques for matrix product states. And with these techniques, we can calculate the transport properties. These figures show the energy current as a function of chirality. There is one point where the energy current is large. Different lines show the energy current for different system size. Different plots show the energy current at different F values. We are always working in the ordered phase, by the way. Different F values and different and one of these plots show the for the results for a slightly tweaked Lindblad operator, which qualitatively has the same property. The goal of trying that out was to make sure that the results that we're getting is not an anomalous result due to some specific form of the Lindblad operator. Now, there is a place where there is a point in the theta plane where theta axis where the current is very large. You would guess that is an integrable point, and indeed it turns out to be, thanks to analytical work by Barry McCoy and others. And they've shown that there is a line of integrable points, j cosine 3 theta is equal to f, along which you'd expect a line of integrable points. This plot shows the current as a function of theta and f. The color indicates the current, and f, the two axes are f and theta. The line along which there is a large current that exactly corresponds to j cosine 3 theta is equal to f. And so our numerical results do match with the analytical result. Now, the main goal was to check how the scaling exponent changes with theta. The scaling exponent is exactly 0 as expected from ballistic transport at the integrable point. Away from the integral point, the scaling exponent calculated from the current turns out to indicate something like superdiffusive transport. But we looked at it more carefully. It turns out that if you plot the conductance instead of the current and obtain the scaling from there, we get something much closer to diffusive transport, which is less surprising. So bottom line is, so the summary is that using quench studies, we can say that theta affects the entanglement growth and thermalization at the edges. Sorry, this should be large. And theta also affects the transport properties. And along a line of, in the theta f plane, there is a set of integrable points. And all along those points, we find ballistic transport. And away from that, we find something that is consistent with diffusive transport. For further studies, we are thinking of doing root weight calculation and asking what happens if we play with the phi parameter, and what does that, what physics does that bring in. Sorry, I hope I didn't go over time.
Well, we are just in time. Thank you, Srijit, for a very nice talk. So we are actually a bit pressed for time. So unless there are some pressing questions, we can move on to the, yeah, Arnav has a question. So maybe we'll take that.
Yeah.
Arnav, please go ahead. Yeah.
Yeah. So Srijit, so you talked about this McCoy result where they found this line of integrability with theta,
Yeah.
right?
Yeah.
But
Yeah.
if I understood you correctly, when you're doing these transport calculations,
Yeah.
these
Oh,
obvious
sorry.
that remain.
Sorry, Arnav, you are breaking up. Could you?
Internet. Can you hear me now?
Yeah. Yeah.
Okay, so let me repeat. So you talked about this McCoy et al. Results, right? So where you talked about this integrable line in theta, right? But when you use these Lindbladians, whatever forms that you have used, is it obvious that the system still remains integrable? Is there a way to understand?
So the transport is determined. You know, the Lindblad operator has a very small support. You know, it has a support of 4 sites in total in a chain of 48 sites, and we are essentially.
Oh, I see. So this is just boundary driven. That's what you're saying.
Yes, yeah. These, yeah. That's the full Lindblad calculation is impractical.
I see. Okay. Yeah. Thanks. Yeah.
Okay, so maybe we can move on to the next talk, and thank you, Srijit, for a very nice talk. Okay, so the last talk of the session is by Professor Anatoly Polkovnikov from Boston University. And Anatoly, could you please share your slide? Yeah, and he's going to talk about perturbative Markov construction of the slowest local operator. So Anatoly, please go ahead. Anatoly, you are muted.
Is it good now? Sorry,
Yeah.
I forgot to unmute myself. Can you hear me now? Hello?
Yeah.
Okay, well, sorry about that. So,
okay.
I would like to thank organizers one more time, unmuted this time, for inviting me. It's actually my second visit to Kolkata, virtual visit to Kolkata recently, and this talk will be related to what I was presenting, but I kind of changed the focus a little bit. So last time I presented a talk where I focused on sort of explaining why existing evidence of many-body localization is not, I would say, convincing. This time I would try to focus on a very specific and well-defined model, which I think highlights both how thermalization happens in the setup where things normalize slowly. In this sense, my talk will be very much related to Arnab. And if I have time, and also I will try to highlight what was the main issue with MBL theories. So they overlooked some very important piece of physics. And then if I have time, I'll still come back to numerical evidence and show what's wrong with that. So I'm not trying to prove rigorously that there is no MBL. It's difficult, but I'll show that things are much more unstable than people thought. Okay, so most of the work was done actually with Dries cells, so even by Dries cells, he did more than myself. So I usually highlight many courses, but for this particular thing, it's mostly work of him and a little bit of myself. So as I said, there will be some overlap with what Arnab was talking, and this is basically a question of how chaos emerges. And in classical systems, we know that it emerges gradually. So this is like a snapshot of trajectories of a nonlinear oscillator, and if nonlinearity is weak, we see sort of very nice trajectories, even though the model is non-integrable. While if we increase nonlinearity, we immediately see chaos. And there is a mathematical Cam theorem which tells us that we need a certain threshold. And as Arnab explained, so the reason why chaos doesn't appear right away is that we have sort of dressed integrals of motion. So let me also highlight a work which was led by a former student at BU, Mohit Pandey, where we looked and tried to understand what is sort of generic mechanism of emergence of chaos. And we used fidelity susceptibility, or basically sensitivity of eigenstates as a measure, like sensitivity of trajectories is usually used in classical systems, but there is no natural notion of trajectory in quantum mechanics. But we can sort of do the same thing and ask how eigenstates are sensitive. And in generic systems, and generic means there are no large scales. Like in case of Floquet, generic will mean that we have frequency of the order of 1, but we say have small driving amplitude. So what we found that in basically all models we looked at, there is a similar scheme. So we have system size. These are local interacting models. We have integrability breaking parameter, and we typically need log scale. So it's very small, exponentially small, the system size. And then we have 3 regimes. So when integrability breaking is big, we have ETH regime, and there our chi, our fidelity susceptibility, grows exponentially with system size. And if you want, entropy defines Lyapunov exponent in space. When integrability breaking is very small, we have very small susceptibility. So in the sense that our states are very, very robust. And this is sort of how systems fight the problem of small denominators. And the interesting thing, which was unexpected, that we found that there is intermediate regime always, which is in some sense maximally chaotic, maximally sensitive eigenstates. And there Lyapunov exponent is given by twice entropy, and this saturates the upper bound. But generically, we found both lines are exponential. One is faster than another. There is like very interesting not understood physics, but this is sort of the story. But in this talk, I want to focus on more interesting situations, and this is rather specific setup. So I'm not, again, trying to generalize that all interesting situations are like that, but this is a scenario which we understand. So let's imagine that we have some many-body system, and this is sort of a local bus, and I will make some assumptions about the bus. And then we have like a simple 2-level system which we want to couple this to this bus with strength epsilon. And we assume that epsilon is not very big. This is actually probably not important, but at least for analytic construction it's important. But we will have also impurity potential, which is large. So, and these are basically the assumptions we use. So BAS has finite local bandwidth, so it's spin system. And I'll show, of course, specific examples, which basically means that we cannot absorb this energy locally. So we really need to distribute this. If you want to thermalize impurity, we need to distribute this energy over large distances. Well, as I said, we will have small epsilon. This is just to control analytic calculations. As I'll show numerically, it plays no role. And we have this large local energy scale. So, and the questions we ask, how does this impurity relax? What happens to the dressed local integrals of motion? It's sort of analog of Floquet Hamiltonian, which Arnab mentioned. And then we can ask, like, under which conditions does the impurity thermalize? So what we need to require about the BAS. And I don't want to assume anything about eigenstates. So in fact, eigenstates will never appear in this talk. So I'll show some numerics, I'll show some analytics, but also some numerics. And for numerics, we use specific models. So basically, the first part is the same. Then coupling to the bus will be always to a boundary spin. We take a transverse, but longitudinal plays no role. I can absorb it to each bus. I just don't want to go into details. So anyway, and for ergodic system, we can take XXZ XXZ spin chain. For numerically, we do one-dimensional studies. Actually, the same should work classically, and classically one can study higher dimensions. Anyway, then we introduce small disordered magnetic field. It's really small in the sense that no one questions this is ergodic ETH system, so magnetic field breaks integrability, but it also allows to average numerical results a little bit. And another setup, which I will show, it's like typical MBL setup, or at least not typical, similar. When we have periodically in subsets of the spins, we have also strong magnetic fields, strong disorder, if you want. So, and I will try to convince you that basically there is no difference between 1 and 2. And as I said, I don't want to make a single assumption about what eigenstates of H bus are doing, whether they are localized or delocalized, and so on. Think about this. We work in thermodynamic limit. So there is, as I said, direct analogy with Floquet, and this can be seen by just going to rotating frame with respect to this large scale. So if I go to the rotating frame, basically a frame where S0 rotates with frequency V, then this field disappears. But because spin rotates, my coupling to the bus becomes time dependent. It's time periodic and it oscillates with high frequency. So we map the static problem to the Floquet problem, right? And if we have Floquet problem, we immediately have expectations about how this impurity will decay in thermodynamic limit, right? So if we drive something with high frequency, well, the first thing we are taught to do and what we should do is to write Fermi golden rule rate, right? So we have perturbation of small amplitude, right, and high frequency. So then we want to know what's the decay rate of this impurity, right? It's given by the spectral function of this operator. It's proportional to epsilon squared, obviously. And then we just say, well, at long times, this impurity should decay. And I'm not proving it. I'm just saying this is like our standard sort of understanding how would we approach it. And then there is a very simple way to estimate this gamma. So because we cannot absorb large energy locally, then we need to sort of excite V over J links, right? And each time we do it, by perturbation theory, we get J over V suppression. So if we combine this in one dimension, we will get this expression that gamma is proportional, obviously epsilon squared, but it's also exponential in V with extra log. And more careful work actually showed actually it's very recent work, and I'll mention it in a second, related to operator spreading, Krylov complexity. They actually strongly argued why this is correct statement, and even there was a paper by Cowell who proved it vigorously. And in higher dimensions, it's expected to be exactly of the same form, but just exponential. This log is really one-dimensional figure. I don't have very simple argument why it's exponential, so this argument only works in 1D. So, and then we immediately see, well, in this setup, we will have localization transition inevitably when this Fermi golden rule really becomes level spacing, right? Because then we just cannot decay. And from here, we just see a very simple criterion that critical V scales as L. Well, more carefully in 1D, it's L over log L. So if you have 2D, we won't have this log. Yeah, so at least we know that when V becomes larger than this scale, we have to be localized because simply there are no states. There are no continuous states. Well, we can check whether it works. We used, say, the same metric, fidelity susceptibility, for this problem, like single impurity. And then if we do numerics, so we look into fidelity susceptibility. Sorry, I erased this scale as a function of V. We just see that as we increase system size, go from red to green, we have a shift. And if you try to plot maximum as a function of L, we will see basically a line. So V indeed changes linearly. For small system sizes, it's impossible to see log. So from numerics, we just cannot see whether log is there or not. But anyway, this seems to be a consistent picture. So now we can ask, what happens if we start adding more impurities? So we have still one boundary impurity here, but we also add more impurities here, like is a 1 or 2. I mean, then we ran out of system sizes. And then actually, if we study same spectral functions, same Fermi golden rule rate, we see nothing much changes, except that we start to see these jumps. And the origin of these jumps mean that we absorb less, right? So it's a log scale. And the origin of these jumps is sort of simple. We had weak links, right? So if we want to distribute large energy, we really have to invoke this weak links time of the time, because this piece cannot absorb very high energy, right? And then you immediately see that from the same argument I showed that this just renormalizes tau. So this tau, which enters Fermi-Golden rule rate, gets dressed by sort of inverse density of impurities, but nothing else changes. And moreover, this tau is renormalized by at most factor of 2, right? Because distance between impurities is not bigger than 1. So basically we get same criterion. So now we need a bit smaller impurity base is a little bit less, more localizing. So we get this extra factor in denominator, but we still have same extensive scaling. Again, this is just as efficient. So we know that at this point we have to be localized. So far we don't say what's happening below this point. But I just want to say that from this argument, if we study Fermi-Golden rule rate of spectral function, in thermodynamic limit, nothing really special happens at any finite V. So there is no special disorder, at least from this point of view. Okay, so now let's try to come from the other side. So let's try it from localized regime, which either means short times in thermodynamic limit or small l. So it's the same problem. But now we will try to find what is the best conserved operator. So SZ0 is almost conserved, but can we do better than that? And so what we are trying to do is to perturbatively construct what's known as LIOM, local integral of motion. So basically we want to find operator Q which commutes with H and which is adiabatically connected to SZ0, right? So we will use first order in epsilon and then we'll try to do all orders in 1 over V. So in this sense, we work in thermodynamic limit. Okay, so what we do, we just write Q is a, oh, I don't know why it's SZ squared, so it should be SZ0. We write Q as a power series in 1 over V, so we say it's SZ0 plus 1 over U Q1 plus 1 over U squared Q2. So in general, Q1, Q2 are functions of this epsilon, but as I said, we want linear order in epsilon. And this should connect to FGR. If there is a connection. So, and then we just write, this is what Birkhoff construction is. We just try to write this recursive relation. So next order commuting with large term, SZ, is the same as previous order commuting with small term, not proportional to V, right? So let's see how it works order by order. So our zeroth order is SZ0, right? And then we see that next order commuting with SZ0 should be previous order commuting with H int. SZ0 commutes with H bus by construction because H bus knows nothing about SZ0. Well, you just stare at this expression and you see immediately first order is just my H interaction, so my coupling to the bus. Okay, let's try to do next order. So I'll do Q2 SZ0 should be the same as first order with this guy, but again, H int commutes to H int, I only get H bus. So this turns out to be a little bit more subtle, but you can still do it. So I don't want to go to details. You can just write that commutator, Q2 will be a commutator of H bus and H int, and there is one extra commutator with SZ0, which is not that important. But at some point, there could be some terms of the order of epsilon squared, right? We can always add them to Q2, which commute to SZ0. So there is some freedom. And it turns out that this freedom makes the whole construction very complicated in general. But if we do first linear order in epsilon, all these terms can be ignored, then actual construction is easier. So in the next term, we will get next order commutator. So we start to getting nested commutators, same as Arnav mentioned. And if we keep going, we can get basically an exact, again, in first order in epsilon construction. So, and this construction basically gets in nested commutators of H interaction, so coupling to the bus, and H bus itself. So this add means I use nested commutator 2Q times. So there are some even odd terms, but it doesn't matter. So that's exact. And then we can ask how good we are, right? So how good we are can be quantified by commutator of Q and H, which should be 0. And we find norm of this commutator. And you can probably believe me that if we do this construction, we cancel all the terms except for last, right? Because we stop construction at order n. And there is only one term in this commutator, which is basically next as commutator of this order to n plus 1 divided by v. Okay, so that's completely general result. And I just want to highlight that for finite dimensional systems, this is convergent because norm of this nested commutator, it's finite dimensional matrices, it's constant. And each time we get higher and higher power of V, there are no factorials or any other terms here. So it's a convergent expansion, and we can get like exact integral of motion like this. Right? But we are interested in thermodynamic limit, where we have to be careful with norms. And then we again invoke this very recent work, which started in Berkeley group and then was continued by several other people, the names are there, who realized that for generic chaotic models, again, with no assumptions of eigenstates, these norms of nested commutators grow factorially. So this norm of this nested commutator of order k is basically 2k power 2k. This log is really 1D feature related to this log omega I mentioned. It's not that important, but the leading asymptotic is 2k power 2k. So it grows fast. And it turns out that this is the same parameter tau which enters FGR rate. So these things are related. And I know it could be fast, but let me just spell it. So this relation is basically because FGR rate is a generating function of these moments. So same matrix elements of diagonal matrix elements enter. So essentially, I can say that this norm of nested commutator is integral of FGR rate times omega power to k. This is exact relation up to some factors of pi and so on. And then we just see at large k, high frequency asymptotic of FGR rate determines this. And if you take saddle point, this implies this and this implies this. So they're really tied together. Okay, but now you see, we see this is a divergent series. And then we can, our best integral of motion, it occurs at finite n. So we can just do a saddle point approximation, find that this finite n, where we get minimal decay rate, is essentially scales as V log V. And then if we ask what's the lifetime, short lifetime of this guy, it turns out it's square root of FGR rate. And this is an interesting result. So we first thought that, well, something is wrong, but dimensions are fine. You know, FGR rate contains extra delta function of energy, which gives you dimensions. So, and there is indication we didn't check yet that this slowest operator sees Hamiltonian as a random matrix. So in this sense, we expect that this best conserved quantity will universally decay in time. And then I want to highlight, this is a really important point. This divergence is entirely due to virtual processes. There are no resonances here. And if we have non-interacting baths, the radius of convergence is finite. Then these guys don't grow factorially. So this is a really important point. Okay. Well, can we go beyond perturbation theory? Well, we can upgrade perturbation theory to variational ansatz. So it turns out in leading order on epsilon, this nested commutator ansatz is just exact. It's complete operator ansatz. So we can just basically, instead of doing perturbative results, we can say, let's just do variational calculation. Again, I don't want to go into details, and I want to minimize this commutator. And this is a numerical result, which just basically shows what's going on. So solid lines of perturbation theory, they start to diverge. Of course, variational theory cannot diverge because if you add more parameters, you can only get beta commutator, right? But what you see that variational calculation goes a little bit quicker than perturbative. Yeah, we don't know exactly the scaling, but roughly in the same way. And then when perturbation theory reaches the minimum, variational is stalled. So basically we cannot improve. So best perturbative result is the best result essentially. And what you also find that there are many, many degenerate solutions, nearly degenerate solutions here. So this means that we basically start mixing with other states. So after this order, we start decaying essentially. So one can ask, okay, what about disordered systems? So we didn't do calculations for this impurity model. There's many impurities, but we can steal results from disordered models, and this is from Perimeter Group, very recent paper. So they plot Pilov coefficients, which basically logs of this nested commutators divided by n. Let me not go into details. So, and they find that with as you increase disorder, you go to the same asymptotic form. So it's, if you want, in my notations, just tau changes. So a small n, you start to see some differences, but asymptotically at large n, large order of nested commutator, you go to the same form. So in this sense, whether you have disordered systems or not, doesn't matter. You are equal and stable. So perturbatively, it's unstable. So I don't know if I have, do you have 5-10 minutes or how much?
You have roughly like 8 minutes.
Okay, so I have time. So let me just go through quickly through sort of MBL evidence and show that what was wrong. Like we had like 15 years, I guess, of people claiming there is MBL, they saw numerics and so on. And it turns out it was like, I don't want to say 15 years of mistakes, but there was basically one big issue in the whole thing. And even David Hughes admitted in his talk, even though he still believes there is MBL. So the idea is that this is localization in Fock space. So we imagine that our Fock space is like, I don't know, spin up, spin down, or charges here, charges not here, right? So we have like huge Hilbert space, and localization is basically pictorially is that each Fock state is sort of connected to few states. There are more complex now pictures of MBL. Let me not go into this detail. So like last time someone asked me this question. So, but let me just focus that there is an apparent, I think, common mistake is that there is assumption that virtual transitions are harmless and focus on resonances. And as I said, this only works for non-interacting models. So let me just go through sort of existing evidence. So most people studied disordered Heisenberg chain, same I showed before, but with larger disorder. And they studied level spacings, and they saw like nice level crossings at disorder like 3.6. They looked into something which is similar to fidelity susceptibility, ratio of off-diagonal matrix elements and energy denominators, and saw that at critical disorder, this thing qualitatively changes behavior and so on. So basically for quite a few years, like between, I would say, 2006 or 2008 and 2018, there was like complete consensus, or almost complete consensus, that there is a transition at 3.6 and so on. But then in 2019, basically the situation started to change. There was now famous paper by Tomasz Pradzen, which was rejected from all top journals, of course, who actually said that if they study ratio of Heisenberg time and tau-less time when you cross over to diffusion, then actually there is much better scaling collapse if you plot it versus W over L instead of W. Again, logs are impossible to see in the system sizes. There was immediate rebuttal, but things continue. So let me go to a bit later. I jump over skip some important papers. So one is basically very much related to what I was telling you, like finding the slowest operator. And there was a paper by Morningstar et al. And in the original version in 2020, they concluded from the drift of this lifetime, basically a decay rate, which I was talking about, that transition cannot happen below 7. And then following this Sells work, which I show in the next slide, they actually they updated the paper and concluded transition is at least at 18. And then there was also beta numerics. So this is probably the best numerics I know by Piotr Sirant and Kuba Zakrevsky, who like developed some algorithm which I don't understand, but I heard from many people it's really spectacular. So they were able to reach system sizes up to 200 and times up to 10 power 3. And you see at disorder 8, they see persistent drift. It's small but persistent, so this is imbalanced decay. And interesting, it's unimaginable to me. Their paper was rejected even from PRB. So this really tells us something is wrong with MBL community. I mean, one thing you don't change beliefs, and another you just block other people from publishing numerical papers. So, and from this you already see that tau-less time is like at least e power 35. And then there was a paper by Dries, which I mentioned briefly, which followed paper by Morningstar, who basically studied same scale decay rate. You multiply by 4 power L, because just was argument by De Roock and Houveniers that if you have a transition, this combination should be below 1. And then he's found that if you change this order between 8 and 20, so this is what people thought like MBL rate, then you see very clear signatures that sort of this ratio reaches the minimum of starts diverging. So this is basically, he found lower bound for MBL, it's 22. It's a bit less conservative than 18 by Morningstar. And this implies that tau is time. So time before you cannot even see critical slowing down, right? It's already like e power 70. So right now, at least it's absolutely clear that even if for some mysterious reason there is MBL transition, it's not ever observable either numerically or experimentally. And of course, you're probably not surprised by the now his paper is also rejected from PRB. So it's really unimaginable. Like best papers with best numerics are not even like, I don't know who are the referees, obviously, but they're not allowing even in PhysRevB. It's the first time I see this in physics happening. So last slide. So what about previous papers, which were published, well cited, and so on? These are well-known MBL experts who claim that they also study lifetime and study and claim that they see exponential scaling. Well, this is a paper from this group in 2016, who basically said that they see exponential scaling at large disorder. What rho means doesn't matter, it's lifetime. So think about this as lifetime. But if you just digitize the data, you actually see there is a curvature. If you digitize the data and subtract the slope, it's basically what Dries and Morningstar did, you will see that it's not just saturating the slope, it's actually departing super fast from the line. This is, if you want, at least this part is a parabola. So actually, if you analyze this data honestly, you will conclude there is no exponential scaling. It's slower. Well, there is another paper by also famous people like David Hughes, Ignacio Chirac, who also claim exponential scaling. So if we take largest disorder, 9, so which was believed like deep NBL, and also subtract slope, we see it's actually not, well, you just see it with your eye, right? The straight line is misleading, so there is a curvature. So if you supply, you see parabola. And the slope doesn't even decrease if you increase disorder. So this is always there, it's persistent. I think I ran out of time, so let me just say that we started at least this work, I'm going back in history in 2020, motivated by work of Ljubljana group. And the conclusion which we find that this system is actually a glass in the sense that, or at least close to be a glass. Instead, if you look into spectral functions, we will see 1 over omega behavior, which indicates log and time decay, and so on. So this is a very interesting phase, and my understanding like connection to this Birkhoff construction, Lioms, is still in the air. So let me summarize. So there is a connection between the FGR decay rate and Birkhoff construction. So they really match with each other very nicely. So for generic bass, this local integrals of motion are unstable. And I just want to emphasize again, I didn't make any assumptions about eigenstates. You can add temperature there. And instead of like infinite temperature norms, you can use finite temperature norms. It's believed that these norms of nested commutators will behave in the same way. Just tau will be temperature dependent. But again, this has to be studied. And the same, by the way, can be done classically. We will have nested Poisson brackets. So I think there is very nice potential to make connections between quantum and classical chaos. So there are many other systems. So disordered systems are not really special. They're interesting, of course, but they're not special. And we heard about Floquet systems from Arnav, the scars, Fermi-Pasta-Ulam type problems. And there are many, many examples. Yeah, I don't know how to properly define word generic, but if you have like good scale separation, you probably will have similar physics. Again, whether there is always transition or not, I'm not making any claims. And localization, coming back to MBL, is likely unstable in thermodynamic limit. I would say there is no evidence for MBL in literature, really none. we went through all the papers. I think we didn't find any single one which doesn't have issues. But instead, there is evidence that these systems are interesting glasses. Okay, thank you very much for your attention.
Okay, thank you, Anatoly. That's a very nice talk. So there are some questions. First, let me read out the ones that we found from YouTube. So, okay, so this is from Saurabh Suresh. And the first question is that, are there non-perturbative methods that can study the possibility of NBL phases in impure spin chains?
Well, yes. So in a way that what I showed was already non-perturbative result, right? It's perturbative in epsilon, but it's non-perturbative in V, right? So it's like when you optimize perturbation theory, you get an order of perturbation theory which depends on perturbation itself, right? So and then you get basically a non-perturbative results. So this gamma is exponential in V. Now one can ask, so do I need perturbation theory in epsilon? And the answer is probably no, but we didn't get there yet. So one can now do construction order by order in epsilon. And I showed you numerically, at least, it doesn't look like we need the small order in epsilon. And finally, well, I briefly presented this variational calculation. And this is really non-perturbative. So we have this complete operator ansatz, and we basically solve variational problem. It turns out that if we use this norms of operators, asymptotic norms of operators, this is algebraic problem. Because we know all the entries, so we can minimize commutator of Q and H, and this is bilinear function of these alphas. So, but we so far couldn't find an analytical solution. So it's basically a problem where you know entries of the matrix very well. It's a very simple matrix with this variational approach, but it has like coefficients which are sort of crazy functions. I mean, this factorials over exponentials and so on, and we don't know. But it's not impossible that one can solve this problem analytically. It's a well-defined, just want to highlight maybe again, it's a well-defined mathematical problem where the only parameter which enters is this tau. Nothing else.
Okay, the second question is basically, is it possible, from the same person, is it possible that the numerical experiments are not able to show NBL due to numerical instability? Okay.
Well, of course, everything is possible, but there is a lot of evidence. So you see, when we try to do, well, first of all, you should ask, of course, the authors of numerical papers, and usually they really check for numerical convergence if they do it accurately. But also, even here I presented like, I don't know, very different numerical methods, which kind of agree with each other. So I didn't mention that what we were doing with fidelity susceptibility perfectly agreed with what Ljubljana group was doing with spectral form factors and so on. So this numerics by Piotr Sirant and Kuba Zakrevsky, it's kind of stands alone a little bit because no one, as far as I know, was able to go to these system sizes and these times. But at least they made sure they compared with existing previous numerics, and they agreed. And they spend a lot of time checking that their results converge.
Okay.
But, it's not my work, so I cannot, of course, comment more.
Sure. Yeah. Okay, so let's now come to the questions from the speakers in this Google Meet session. So the first person to raise hand is Arnab Dash. So Arnab, please go ahead.
Hi, Anatoly. It was very nice talk.
Hi.
I was just asking, wondering about the meaning of this divergence, which just comes from explosion of the virtual processes. Like you have similar kind of divergence also in the QED, for example, dating back to the time of QED. So, but you know, I mean, this series can be asymptotic. I'm not talking about MBL. I'm very convinced that MBL is not stable. I'm just talking about in general. So you can have these processes where first few terms are actually the right representation of the correct results, and the following divergent part is not really, like in general asymptotic series, what happens in QED actually. So you cannot, it's a divergent series, right? Dyson proved it. So, but none, so all you do is getting out of the resonance is like equivalent to do the renormalization. The renormalization in QED just gets off the resonance from individual terms, but the sum still diverges because, as you said, I mean, the number of virtual processes explodes. So is it possible that when we see a divergence, we just don't straight conclude that something is actually going to, it has a real meaning? I mean, it might not, right?
Well, no. I think there is a real meaning. So that's why we kind of, in the end, with this converged to the simple problem, which is not even MBL. It's one impurity coupled to a Bass. And with this problem, we can sort of understand many things. So I didn't include all of them into numeric. So you have to ask the right question. So, for example, let me just check this impurity, the strong magnetic field, not connected to the edge, but connected to the middle of the sample, right? That's even a simpler question. And you can ask, what Schrieffer-Wolff transformation will tell me? And at the end, what I'm telling you is that Schrieffer-Wolff transformation exists only up to finite order. And after that, we cannot do it. Well, Schrieffer-Wolff transformation tells you there is a virtual hopping across impurity, J squared over V, right? If you go to higher order, you get better and better virtual hopping. And this, in a way, is exact procedure for, or I mean, as exact as you want for studying a transport in a chain. I mean, if you include high order transformation, you'll get small correction to a transport coefficient. So in this sense, physics is not really affected by divergence.
All right.
But we can ask a different question. What's the lifetime of this impurity spin, right?
Right.
And for this question, actually, this divergence is crucial because this tells us that in Schrieffer-Wolff transformation, where this impurity has infinite lifetime, this is basically a finite time result, which actually makes sense because if you couple to ergodic Bass, you know that sooner or later the charge will decay. So, and this means that in your transport, there will be a small correction due to decay of impurity. So if you really study very long times, like exponentially long times, then you got your transport not entirely correctly. But when we study a question about stability of local integral of motion, this is the only question we are interested in, right? So in this sense, in MBL, we are actually exactly asking this question. Is what's happening after a very long time? Because we know at short times nothing happens, system is localized, so no one really questions it. So in this sense, I don't want to comment about QED, I don't understand it well enough, but at least from this point of view. But my understanding that always you need to ask which question you're asking. For some questions, these divergences just don't play a role. If you want, they're pushed to infinite times, like times which we don't care about, or they have like a very small effect. So even if impurity decays, the effect of conductivity will be tiny, right? So we will get extra one transported charge in a sample. So after exponential long times. But for some questions, these divergences are important, and I think with Floquet it's very similar.
Okay.
It's not. We'll discuss it later at some point.
So maybe in the breakout room after this, if you guys are up to it. But let me just take one last question from Srijit, and Srijit, please go ahead.
I have two very short questions. In the plot that you showed, the x-axis is the truncation order. What are the different lines?
I forgot to say, this is different V. I apologize. I forgot to put it. So this is bigger and bigger V. So bigger and bigger magnetic field on impurity.
Okay.
So this V, you see, this norm goes down more and more, which means that we have better and better conserved quantity. Right?
Okay.
But they always, we always reach a minimum. And variationally, we reach not a minimum, but we reach a plateau. We don't know what this tail is. It's not explained. It's probably 1 over n, some slope polynomial, maybe related to diffusion. This is something we don't understand, but it's almost flat.
And the question I had is, so the result that you showed is for MBL in steady Hamiltonian. Is the result, is a similar idea true even for the Floquet MBL?
I don't know. No, I don't want to say more than I know, because in Floquet you don't have local coupling, right? You are driving all spins together, and one has to repeat this construction. So it's a little bit more subtle. It looks like it's very easy to solve this equation. I just basically showed, I need to invert it. But it turns out that this can be only solved if this operator on the right-hand side is odd under parity. So basically, if you write z operator as z, you'll get minus this operator. And all difficulties come of adding these dots of the order of epsilon squared, which make this operator odd. So like here, if leading order in epsilon, it's odd automatically because h bus is even, it doesn't know anything about the z, and h int is odd, it just has a sec. So this is a subtlety. And because of that, this construction is not as obvious to generalize. So it's highly likely that if we do Floquet problem where we drive every spin, right, we apply we drive time-dependent field to every degree of freedom, it's very likely that something like that can be constructed, but one has to work it out. It's much harder problem than I thought initially, because inverting commutator is a difficult problem.
Thank you.
Okay, so let's thank Anatoly for a very nice talk, and let's also thank all the speakers of this session. And with that, let's end this session. Thank you.
Okay, just a final announcement. So breakout rooms have been created, but you can also stay here if you want to discuss. And if you want to go to a certain breakout room, just put you there.